Hi, everyone. I'm Susan Nash, AAPG, and it is a special treat today to have Andy Pepper, who is all about petroleum systems. He is here to talk to us today about some thoughts on petroleum systems and future prospectivity of the East Venezuela, Trinidad and Tobago, Barbados, Guyana, Suriname region. And it's super exciting. He's going to focus on gas, which just makes it really pretty unique. So Andy Pepper, if you don't know already, is director of This is Petroleum Systems in Fredericksburg, Texas. He's also an adjunct professor at the University of Houston. So I'd like to invite Andy to share his screen. And while he's doing so, I want to just remind everyone that you will be getting an email from me with a link to the recording. And just want to thank you for being here. So thank you, and you have already shared. That's true.
Yeah, I'm shared already, Susan?
Yes, you're here. Yes,
Okay,
it's me
cool. All
sharing.
right, great. Okay, well, thanks very much, Susan, for the invite. I really appreciate it. I thought we'd do something slightly different here in that with gas being the transition fuel to the future, in my view, then we don't talk about gas exploration or concepts in gas petroleum systems very often because we're often focused on the oil. So this is really going to have a slant towards the small molecules. I'd like to just acknowledge up front my associates, Lara Heister, Andres Cedeno, worked with us on a Suriname project. He's now with Equinor. Jean-Marie Legel, who builds and designs and runs the AI-assisted software that we use these days. Then shout out for some researchers, Brian Moore. I'll show some of his work on Barbados. He's now with Total. Kenneth Schipper will show some of his thermal modeling work in the Suriname, Guyana area. And then Danielle Easley, I just want to give her a shout out as well on her project, which we'll kind of highlight as we go through. So let's go to the next slide. So yeah, we're going to talk about source rocks to start with, because that's where we should start in the petroleum system, obviously. And then looking at some origins of petroleum fluids with an emphasis again on the gas. So we don't talk very often about biogenic gas. We'll talk a little bit about some of our latest models for biogenic gas. And then look at a case history from Trinidad on understanding the causes of the oil and gas trends there. And then take a quick look at the Guyana Basin thermal modeling from Kenneth. And then just something about phase behavior. This seems to be a subject that a lot of geologists seem to leave to reservoir engineers or generally don't feel confident about. But I want to show you something there about how we can understand, use simple phase envelopes to understand the origins of fluids, including the so-called volatile oil that's being interpreted in Suriname. So let's go to the next section then. So the main point, it's kind of frustrating. If you've been following the work we've been doing, I've been sort of pointing out that we don't really know very much about the true ages and distributions of the world's source rocks. And in this part of the world, you'll hear people say everything's La Luna or Cenomanian, Turonian, and there's much more to it than that. And if we don't get the source rock right, then all the other elements of our model construct are going to be compromised. So yeah, so basically, I'm going to offer also an update to our understanding of Trinidad source rocks, where supposedly the Naparima Hill source rock is the source of, if you read the books on Trinidad. Okay, so let me see if I can go. Some reason. Oh, there we go. It's going back. Yeah, so let's take a quick look at the Demerara rise. This is public data, and I'm going to show almost all public data here. And where I don't, I will credit the folks that have allowed us to use their data. This is basically the DSDP on the Demerara high. There's a transect of wells starting in the basin, coming up onto the crest of the high, which was a big inversion anticline during the Middle Albian, during the breakup unconformity. and then coming across down into the basin again. If we take a time series, so in the Excalibur software now, we're able to transform our source rock model into a time scale. You'll notice here the vertical scale is millions of years, not necessarily depth. And what we're looking for here are the cycles and correlations of what we call these global acmes of source rock deposition. So the Cenomanian-Turonian boundary is down here at 93.5 million years. But you can see here there's a lot more to this than the Cenomanian-Turonian. We've got source rock development up here in the coniation, which is very, very strong on the Guyana shelf as well. And the Cenomanian-Turonian source rocks are quite poor on the Guyana shelf. So these acmes come and go depending on the paleogeography of the system. And just to point here that it's not just about the Cenomanian-Turonian, and Daniela Easley's work that she's doing right now, she's doing a transect all the way around from the true La Luna, which again is not just Cenomanian-Turonian, all the way around to these wells that we'll see in a moment that we're talking about right now. Just one kind of shout out for the unsung hero here is the Albion, the 101. These acmes are given their age in millions of years. So the 101 is the latest Albion. We only see it in a couple of these wells because basically, as I said, there's a big high which is being onlapped during the Albion in the post breakup unconformity sequence. But this Albion source rock becomes quite important in other parts of the system. So if we look at a bigger scale here, we're actually looking at the 115 million year restoration and starting to look for these flooding events, these acmes in the Aptian and also in the early Albion, the 110 over here. Jose Gorosabal will be working with him on his work connecting Brazil to Guyana, to Ghana and Cote d'Ivoire in the future. So basically, we've got public data here coming in from Marcio Melo's work, where we're recording, and we're trying to do this based on the source rock data. I think there's a lot of work that's done on oils, and we tried to sort of guesstimate what is the source rock of the oil without looking at the source rock, and I think that can end in tears, as I'll show you in a couple of examples coming up in Trinidad here. So we have the sort of opening of the ocean. The systems become more marine. We've got the organofacies here are annotated with the clay-rich facies versus more carbonate-rich facies as the varying with the paleogeography from place to place. This is a 100 million year snapshot. So this is very similar to the snapshot I was talking about on the Demerara High, where the high is being onlapped. So that's out here. Okay. So and then we open it to the 95 million years, which is the latest Cenomanian, which is the equivalent of the Lower Eagleford, if any of you work the Gulf Coast. And by the way, there is no source rock at the Cenomanian-Turonian boundary. There's one before the Cenomanian-Turonian boundary, the 95, and there's one afterwards, the 93. So again, a lot of the stuff that's talked about about source rocks doesn't really bear very much scrutiny, which is why we're giving it so much attention to kind of go back to basics here and understand the distributions. Yeah, so just come back now to we talked very, very briefly there about source rocks, but let's now talk about source rocks and mechanisms for gas, not just thermogenic but also biogenic gas occurrence. I'll show you a little model that we use for biogenic gas, which is kind of interesting because it depends so much more on pressure and solution than the thermal petroleum system, where the products are essentially insoluble. So here we have a very soluble product, and that's the key, we think, to why biogenic gas is not simply everywhere. I'll show you the model there. We'll talk a little bit about this case history from Trinidad and then the Guyana Basin thermal model. So this is kind of like an idealized filling history of a reservoir. So the reservoir is deposited here and it's buried through the basin. Likewise, the oil front is coming up from the deeply buried source rocks here. The oil front is coming up through time, being pushed by the generation volume from the source rock. And so what happens typically is that there's a reservoir may start its life as a biogenic gas accumulation here above the oil front. Some oil arrives, and so we build a condensate yield into the biogenic gas. And then eventually we add enough oil from below that we form a dew point fluid. So this is the dew point composition versus depth, and this is the bubble point composition. And then from that point onward, the overall composition of the pool is changing like this, but we can't have compositions inside this part of the phase envelope. They can't exist physically. And so we build oil legs down below the gas caps as more and more oil arrives. And then a very interesting thing is we add enough undersaturated oil that eventually we will end up with a solution gas ratio in which really the only way to tell that there was once biogenic gas inherited from here is really to look at the isotopes, or I'll show you some results later on from a compositional model that we use for mud gas interpretation, where also you can often, if you understand composition carefully, you can actually see this from composition too. And then what happens is that the thermogenic front is kind of like a boomerang curve. The thermogenic front, the higher and higher GOR oil, now starts to follow the low GOR oil. And so we go across the phase envelope potentially to, in very rare cases, to dry gases that are essentially all thermogenic dry gas here. So if we think about this filling sequence, everything starts potentially as a biogenic gas accumulation, providing there's a trap there. And as I'm going to show you right now, there are some tricks to understanding why biogenic gas is where it is. I'll show you in a moment. Let me just see if I can move this out of the way. Okay. Right. So what we're looking at here is a series of depth plots, and we've got biogenic gas productivity here in this red curve. Then we have the productivity in excess of the solubility. So this is the solubility, and then the net of those products is here. So in this particular case, we generate biogenic gas, but it's basically unable to exceed the solubility of the water. And so basically we have no, even though we go through the biogenic gas window, all of the gas is dissolved in the water, so we have no biogenic gas accumulation. And we did this to actually do a post-mortem on a giant four-way structure in the Gulf of Mexico that was puzzling, because, why isn't there a biogenic gas accumulation there, even if there's no thermogenic petroleum? So it turns out that it's basically the dissolution and the temperature is really important. So as we increase the temperature, then we change the phase envelope for dissolution. And in this case, with a high temperature case in the basin, we would have some biogenic gas expulsion into the surrounding rocks, but unfortunately it would be deeper than the reservoir. This is the reservoir on structure. This is the reservoir down in the syncline adjacent to it. So basically, the problem is that the biogenic gas accumulation is generated effectively too late and too deep to actually charge the reservoir because of the PVT conditions here. Let's take a look at a prospect. So we have a nearby prospect. We were asked by a client to sort of say, well, okay, if there's nothing in this giant four-way, what about here underneath the salt? So this is the cool case for the thermal prediction from the thermal model, which gives us, again, a fairly negative kind of solution here. But actually, if we change the salinity has a huge impact on solubility. It's basic sort of, school chemistry, right? So if you salt out the gas, then you can form a gas phase. So we can see here in this case, with a higher salinity next to the salt, we would end up with some biogenic gas charging into the syncline to charge the prospect. And if we go to the warm case here with high salinity, we will exacerbate that. So we'll basically bring this more of the kitchen into the biogenic gas accumulation. And then this is a kind of a maximum case, maximum. So in this particular case, we were able to understand the conditions in which the the prospect, the biogenic gas prospect would work, even though the adjacent turtle structure in the basin had clearly not worked. So a lot more to biogenic gas than just getting into the bacterial zone. There's a whole pressure temperature understanding that we need to understand when the gas comes out of solution, because the gas in solution is not a resource, right? It's basically the gas that comes out of solution that migrates to be the resource. Talking of biogenic gas, here's a fantastic study published by Rich Gibson and Leon Zhu back in 2004. This was the former Amoco heartland area before the BP Amoco merger, and so these guys came into the Petroleum System team, and they did this kind of amazing piece of work to understand. So the basin is really deep down here, yet this is where the oil fields are, and the basin is actually coming up shallower here, and yet this is where essentially I think there is only one oil rim in all of these gas fields down here in the gas trend. So what's actually happening? So part of that is biogenic gas. So about 44% of the resources in the oil trend here, if we look at in barrels oil equivalent, is dissolved and capped gas of biogenic origin. And then in the southern trend there, 64% of the BOEs are actually biogenic gas within this trend. So how's this working? Well, the paradox here is that the source rock is actually very deep underneath the oil trend and actually is shallowing underneath the gas trend. And if we look at the thermogenic component of gas here, we've got about 34% of the fluid of thermogenic fluid in the north here is gas, and the rest is oil, which is why it's an oil trend. And then we look at the southern trend down here, typical of SEG, and we have essentially 96% of the resources there are gas, with only a small amount of condensate and oil. So that's at odds with the Beryl history, because the Beryl history is the source rock's actually much shallower down here than it is over here. So how do we do this? Well, the first thing then is if we sort of take a normal picture of, typically a basin modeler will just put in one source rock across the whole basin, and we think that's highly unrealistic, but it is a kind of a thing that people do. In which case we end up with increasing GOR as we go, cumulative GOR as we go into the basin here, because the basin's deeper. But what Rich and Leon did was they basically did a wonderful piece of sort of lateral thinking, as sort of geochemical inversion, saying, well, okay, we know we have shelf facies out here. These source rocks here presumably more subject to oxidation and a lower hydrogen index, versus the ones on the slope toward the basin here, where we would have better preservation and higher hydrogen index. So they basically mapped out a conceptual sort of increase of source rock quality, reflecting that degree of oxidation from the shelf to the basin. And when we run that, we see that we have about 30% cumulative oil in the basin, because it starts off as a highly oil-prone system. And on the shelf, even though it's less mature, we bite into this thermogenic gas charge due to the low HI and the low oil expulsion efficiency of these rocks. And so actually we end up with dry, predicted lean condensate and dry gas. So the system is kind of upside down with respect to maturity and burial depth here, because of this change in facies. And so this is one of the reasons, a great example of one of the reasons why we take our source rock mapping much more seriously than I think we used to do back in the day, because often the source rock distribution can dominate over the maturity picture, as you see beautifully elegant, demonstrated here by the guys. Yeah, other interesting observation while we're talking about Trinidad is that you'll see in the books that supposedly the Naparima Hill is the source rock in Trinidad. So if we plot Naparima Hill is actually a porcellанite, what we call an organofacies A source rock with high sulfur incorporation. You can see those those blue dots there, you see the trajectory of sulfur versus API is very different for these oils. So these oils are from the Pedernales area of Venezuela and the southwest area of Trinidad only. Most of the Trinidad oils, including the ones on the shelf that we just looked at here, are actually low sulfur fluids that clearly do not come from the Naparima Hill. So why, given that the Naparima Hill is supposed to be the source rock, where do these come from? Well, they clearly come from a clay-rich source rock, and basically, if we go to look at the as Daniela's doing right now, basically split the source rocks out into a sort of a slightly older facies, which is often called the Gautier facies, versus the Naparima Hill, which is the porcellanitic, the high sulfur organic matter. Then basically the generally deeper organofacies B, the low sulfur system will mature first, and so that's our explanation largely as to why Trinidad is generally on this organofacies B trends, because the Naparima Hill just doesn't become significantly mature, and we've validated that through some basic thermal modeling. But again, Daniela will be digging into that later on. If we look at sort of pristano-phytanogram, again, we see the same kind of coloring there. The pristane phytane ratio of these oils is around 2, which is a typical marine clay-rich facies value. We see there's very few source rock samples here. The one sample of the Gautier, the deeper organofacies B, more clay-rich source rock is consistent with an origin for pretty much all of those oils. And the Naparima Hill extracts are down here. They're on the organofacies B trend, and as I showed on the sulfur versus API, when we have with GC data, we can see that the pristane phytane less than 1 is again typical of this kind of facies. So yes, there are some Naparima Hill sourced oils in Trinidad, but mostly it's the older formation. And if we look at the biomarkers here, this is a biomarker called gamasserane, and again we see that versus a modified pristane phytane index here. Again, we see that there are relatively few oils are sourced from the Naparima Hill. Most of them are sourced from the older Gautier facies, which is generally of more upper Albion, Cenomanian, Turonian, and maybe a little bit of Coniacian age. So it's the deeper more clay-rich stuff that really is the petroleum system of most of Trinidad. There's some complicated slides here, but basically we're just looking at the thermal stress values inverted from the Tmax data for some published samples. Again, Daniela will be repeating this with a lot more data provided very kindly by the ministry in Trinidad. And so yeah, so generally you see here a lot of these Naparima Hill samples are from the onshore are well before the typical expulsion profile for an organofacies A high sulfur system, and it's really going to be the organofacies B onshore and potentially, obviously, where we just looked with the model from Rich Gibson in the offshore as well. It's going to be the more clay-rich facies that clearly has sourced the offshore petroleum system as well as most of the onshore. Okay, so a little bit of a diversion now, and I'm going to break my rule. I'm going to talk about oil for a brief moment, because there's just something that Brian Moore did for his thesis that is just so cool. It's about the island of Barbados. So those of you that know the area will know there's a small oil field that's developed on the island of Barbados. It's always been a sort of puzzle as to how that got there, given that if we look at the depth of the undergoing plate here, you can see here it's as we saw from the Gibson map earlier on, we see a tremendously deep system down here. So how do we end up with oil near the surface, effectively on Barbados Island? So the answer is, and again, thanks to the folks at BNOC that provided some of the data there. So we were able to build a simple 1D model of the island and basically put a source rock at the base of the Eocene reservoir penetrations that represent the petroleum system on the island here. And then you'll see here, this is basically a kind of a wedge type of model. So we're intruding the wedge underneath this system that is represented by all the imbricates of the older accretionary wedge that's effectively jacking up the island up to the present day. So there's when we look at the temperature data here, the temperature data at the current heating rate, which is partly and again the part of the thermal the heating of the source rock here is actually the warming of the surface intercept water here. So we've got 27 degrees centigrade or so at the surface in the recent burial history, 4 degrees centigrade back here, and so essentially the island is coming up through the sea to getting warmed up as it does, and then getting enough burial here to actually push the oil push a Cretaceous source rock into the oil window just below the TD of the field. So it was the first explanation I'd ever found for why there's a small oil field there. And an interesting, lesson here that, the surface intercept temperature in your basin models can actually can make a difference. So paleobathymetry and paleo temperature important in many ways. Okay, so just a shout out now we're going to go further to the southeast. So there was the accretionary prism, and the Barbados was over here somewhere. This is Kenneth Schipper's map. So compared to the kind of data that Andres and I had when we've been working with Staatsolie down here in Suriname, we've built a petroleum system now in the same Explore Lab software that the U of H students are able to use with an academic license here. So this is a relatively low resolution model in the sense that Kenneth doesn't have all of the temperature control that we had offshore, but he's still done just an amazing job with the data he has. It's a full lithosphere model. We have oceanic crust out here of Jurassic Age and the Cretaceous oceanic crust out here. And this interaction between the changing basement heat flow caused by the basement composition versus the burial history is showing us quite nicely here that as we come into as we come south into the sort of Suriname area down here, we notice we have an increase in gas. We have higher GOR fluids, we have gas cap fluids, and as I'll show in a moment, we have this very mysterious volatile oil that's been stated in the press releases there. So we'll take a look at what's happening there. But basically, the story is that there's a large delta coming in here that is not seen over much of the northern trend in Guyana here, and it's the additional burial plus the changes in basement composition out here that are giving that change in the fluid composition. It's essentially unlike Trinidad, this is largely a thermogenically driven fluid system with very relatively little biogenic gas components. And by the way, I'm able to say some of this because we actually gave a public presentation of after our phase 1 study in Suriname. We gave a public presentation down in Suriname, and so some of these things are in the public record. I certainly won't be divulging anything that we did there which is not in the public record. Okay, so let's take a look then at just the final part here is really the sort of phase behavior and reservoir charge history. I don't know about you, but I've always tried to do my best to decipher what people release in press releases, and I think often people think that they're sort of able to mask the details, but it's actually amazing what you can actually dig out if you sort of know what to look for. So what we're looking at here, these are all press releases. There's no confidential information in here of originally from Exxon, and then in Guyana, and then from Apache originally in the exploration wells in Suriname. Yeah, so I just want to stress that this is something we gave at the LAC conference during COVID. So this is kind of like a prediction, not a. There's lots of after the event petroleum system work goes on, but I want to show you here that you can tease something out that is actually helpful at a relatively low level of knowledge. So what we did here, we just plotted the below mud line. This is the water depth of the well up here, positive, and the below mud line, TD depth. So with this kind of target-led exploration, you know that the TD of the well is generally going to be close to where the reservoir system is, right? Because people don't just keep drilling, although arguably it would be good to collect source rock data by doing that. So generally, we've assumed that the TD of the well is representative of the reservoir. And as we go, I mentioned earlier on, as we go down into Suriname over here, we basically see the wells TD deeper and deeper, and that's because of this wedge of young sediment that comes over the top that basically pushes the system deeper. And there's a strong coincidence here between starting to see the these ambiguous fluids here that were not stated to be either oil or gas, and then there's the fluids that were stated to be gas condensate, like in Haimara here in near the border of Suriname and Guyana, and then we have this mysterious volatile oil or whatever, and then we've got black oil and gas capped oil in here. So these different proportions, but clearly this is a higher GOR system. And the hint as we come to the east of the trend here at Sapakara, that we're actually coming back out of the big sediment wedge that's causing this. So what is actually happening with the phase behavior there? Why is it so difficult to tell whether something is oil or gas? Why do we have this sort of ambiguous hydrocarbons being quoted or this mysterious volatile oil? So again, I want to show a phase envelope, just like the one we showed with the filling history here. And so this is constructed for a sort of default pressure temperature regime, which obviously varies the details of this, but just approximately, it's kind of helpful to look at that. This is for the Lisa well. This is the TD of the well that was put in the press release. So let's assume we have an oil down there. We know it's 32 API oil, but the GOR wasn't stated. But it's rumored to be around 1,000. So what happens here then is that the Lisa fluid is the kind of ideal fluid you want to find in this system because it's highly undersaturated. So in other words, I can deplete the equivalent reservoir temperature by reducing the well pressure to an equivalent burial depth of 2,000 meters here, and I'll still remain a single phase in the reservoir up until that point. So this is really an ideal kind of fluid. If you look at big fields in the Gulf of Mexico, like Mars, it's 1,000 GOR fluid, similar API, but basically the idea is it's a highly undersaturated fluid, and this is a very forgiving fluid when we produce very rapidly in deep water, because we've got a large margin between the bubble point and the actual reservoir temperature. Let's take a look at the Haimara again, that was announced to be gas condensate by Exxon. Again, we can plot the thing just a little bit above the TD of the well, assume the reservoir is somewhere around there. They didn't quote the condensate yield, so this could be, in theory, this could be anything from a very, very rich gas condensate at dew point to, I mean, in theory, it could be a dry gas. We don't know what the GOR is. What we do know is that they've said it's a vapor phase or a gas condensate fluid. Now let's take a look at some of this mysterious stuff, the gas capped oil as we go into Suriname. Apache, if you look at the original press releases there, they had pay counts of what they called oil, they had pay counts of what they called gas condensate, and then they had this sort of mysterious volatile oil stuff that wasn't quite clear what that was or why it was so difficult to tell. But actually we speculated at the time, and I want to just emphasize this is this is from 4 years ago. This is a prediction, not a sort of a retrospect type of thing, where actually what happens is you get closer and closer to deeper and deeper and closer to the critical point. Basically your oil and gas properties become more and more similar, and it becomes more and more difficult to actually tell whether this is a liquid phase in the subsurface or a vapor phase. So presumably this is why Apache had such a hard time deciding or declaring whether this was oil or gas. And so let's take a look at a full data set then. And I want to thank the StatSoli team for giving me permission to show this one slide that we showed at one of the slides that we showed at the show and tell a year or so ago back in Suriname. This is all the PVT data that was part of our petroleum system study. This is all the PVT data, and I've expressed it as a reservoir fluid gas fraction. So this is, you can think of this like the BOE fraction of gas, and it also corresponds very strongly to a mass fraction, which is the way the kinetic models work, where we use kinetic models in basin modeling. And then we're plotting it against the subsurface fluid density. So this is the density that in gram per cc that the MDT gradient would see in the subsurface. It's not the surface density of the fluids. It's the combined molecules in different proportions. And what you can see here is that, just like the diagram we showed, there's a very small gap here between what is clearly a vapor phase fluid and clearly a liquid phase fluid. And you can see that gap here is the white area in the distribution fluids. So these are the so-called volatile oils that were given in the early press releases. They're actually on the other side of the phase envelope. They're actually on the very rich gas condensate side of the phase envelope. But it's a very subtle thing. And one other thing I would rule of thumb I would offer you is that 0.3 weight fraction is about a 3000 GOR, and there's an old reservoir engineering rule of thumb that anything with more than 3000 GOR is going to be a vapor phase in the subsurface, and anything with less than 3000 GOR is going to be a liquid phase, and it works beautifully here. It's just one of those really helpful rules of thumb that I carry around with myself, and so you can look at a press release, just calculate the GOR. If it's more than 3000, then it's almost certainly a vapor phase. It works very, very well. And I see people struggling with trying to use the API gravity to determine what's liquid versus vapor in the subsurface. It doesn't work like that. It basically works off the GOR. And so you can see here that there's this kind of area here. So this gap here corresponds to the gap in the phase envelope that we've drawn on the sort of basin scale back here. So thanks also to I've had to take the well names off here. And thanks to StatSoli for doing that. And I would give a shout out to them that I think they've just taken a most amazing approach with understanding their own basin. So basically, rather than let the operators sort of drip feed an interpretation to them, they brought people in to basically help them understand their own country as a petroleum system. And I think a big shout out to them for giving them credit to do that. And I'm pretty sure they understand their petroleum system a lot better than any of the individual operators there. And that's hard to say for many countries where it just seems to be a kind of a free-for-all where the operators have their own data sets and so on. And anyway, so great shout out to the guys at StatSoli, and thanks for letting us show this data. You'll notice there's some really very condensate lean gases down here. So what's that all about? Because these gases here are basically extremely rich, and even the tops of the gas columns here, these are compositionally graded columns. When you're close to the critical point, there's a strong compositional grading from the top of the column to the bottom or to the contact. So these are obviously very rich, condensate-rich fluids down here. What's going on over here? So the other thing that we we again showed at the show and tell, so I can sort of refer to it, was we have a gas isotope model that involves gas isotopes are again, like a lot of the geochemical tools we have, the plots that generally people use are 30 or 40 years old, and they do not account for the reservoir accumulation processes such as partial capture. You get very different results with partial capture versus cumulative collection of a sort of series of increasing maturity. So in this diagram here, you can see our we call it TIPS mix. It's basically a compositional and isotope modeling profile. And from this model, we were able to invert that this is the Sloania, one of the Sloania fluids here. And again, we showed this at the public presentation. So again, this has already been said in public. But basically, you can see here that we've captured in Sloania, we've only captured the last 75 to 95% of the oil of the maturity window of the gas generation window. And so that's why Sloania is a sort of outlier with a few other fluids out here. It's an outlier from the rest of the fluid system. You can see here that something very different has happened. There's no continuity in composition between these and the others. And so this idea of partial capture is really, it needs to be put into the sort of geochemical playbook, because without it, I see people making really strange interpretations of these things, like, well, we have to mix with gas coming from below from a different source rock. And so it's a lot simpler than that. It's just that not every accumulation collects the molecules from day one. And so if we have partial capture, we get very, very different isotope profiles and compositional profiles. And we can see here that because we missed the early oil, you can see here that the ethane and above content here is less than 1%, right? So you get very different compositions and very different isotopes. Okay, so anyway, thanks for that. It covered a lot of area, a lot of topics, but again, with the sort of hope you found the small molecules of interest. We think Lara and I spent a lot of time working on that from everywhere from sort of mud gas while drilling to these kind of petroleum system fluid prediction studies. But hope you found that emphasis on the gas rather than the oil was kind of interesting. So I think we've got some time hopefully to open that up to questions, Susan.
Yes, definitely. And for those of you who might have been struggling with Zoom, you will get an email with a link to the recording, so that will be available to you. So anyway, don't see any questions in the chat or Q&A, but I would like to ask anybody if they have a question to go ahead and you can open up your microphone and your camera and just go ahead and ask it. In the meantime, I have a question. So my question is, given that what we're finding out now, what are the implications for reservoir connectivity in the existing fields?
Yeah, that's a really good question, because I think in particular, coming back to the graded columns that we see very, very strongly in Suriname, you could end up with a fluid difference between an up dip well and a down dip well, or within from one sand to the other in a reservoir, and you might assume that they're so different that they're not connected. And so, I think that's a really good point, is that often, we just need to understand a little bit more that, often it's not straightforward, or it's not necessarily that obvious what is gas, what is oil in the subsurface, and that all needs to be factored into reservoir connectivity studies. Similarly, with another example I would bring up is that, in that filling history that I mentioned with the sort of boomerang plot back here, where did that go? Oh, right at the very beginning. Okay. Oh, there we go. Yeah. So if the reservoir, I've seen I think I made this mistake earlier on in the Gulf of Mexico with an interpretation of a connectivity study, because basically the biogenic gas that's in this reservoir first will collect in the attic of the reservoir. The oil comes along later. So, because the biogenic gas is lighter than the fluid that's coming in later, it's gravitationally stable. So you end up with an isotopically light gas cap, even though it's in fluid continuity on a precious. So you might end up thinking that, oh well, the up dip well can't be connected to the down dip well because the isotopes and the composition are so different. But it's basically, once you create a gravitationally stable filling system, then it stays that way, and it's really in the thermal system it's different. So when the thermal system, the fluid that's coming in later is lighter than the fluid that's already reservoir, so we end up with reservoir overturning and mixing. And so in that situation, if we've got a well mixed reservoir and we see a fluid difference, then we would suspect a barrier, right? We would suspect a discontinuity in the reservoir, because otherwise, what could have stopped it from mixing? But these gravitationally stable, these biogenic gas mixing systems here can give you these sort of false negatives in terms of reservoir connectivity. So I guess those are two ways, Susan, that I would say that this, understanding the small molecules, if you make that the theme of the talk, two ways that those could send you, in the wrong direction if you weren't aware of those issues.
That's really fascinating. And speaking of wrong directions and complications, how on earth do you tease out the structural aspects, like you showed up close, like the tectonics and the paleotectonics map of Scotese, and then you have like issues of salt. How do you tease out the differences between the impacts of salt and the timings with the tectonics?
Well, I mean, I think I guess the way I would answer that is that we're not makers of maps. We're builders of models based on other people's maps, and so in fact we're looking at a study right now where actually we basically built the whole construct from a series of basic maps that were given to us by the client, plus the well data. And so the Excalibur model that we have right now has got some tremendous map editing and construction. So we don't interpret seismic. It's not our fault. It's not our strength. Never will be. But in terms of that feedback between, instead of building a model and then passing it back to the team to say, is this what you meant? Because often you can make maps that are actually incongruent with each other, and this is a common problem. A lot of basin models will recognize this. They're given maps that look great when you just look at them as separate maps, but then the actual horizons cross over in areas where the interpreter wasn't necessarily thinking that it was very important to do that. But these models kind of force you to address all of those issues that you brought up in terms of fitting the geology, because the geology controls everything. And so you can build, there's only so many whiz bang things and buttons you can press in a basin model, but really it's the geology. And so we call it an earth model now. So I think the idea of a basin model is almost like somebody throws some maps at you and you put them in the software and you get a result. But we're sort of trying to make it much more of an iterative process, so that we can have a dialogue back with the team to say, is this what you meant? And in fact, in the Suriname project, we took all of the disparate individual depth converted areas of the basin, because we had to merge them into a single earth model for the whole basin. And actually we did that within Excalibur. So it's just a great tool for doing that. And then we passed it back and forward to the team to say, okay, is this kind of what you had in mind? And we discussed ways of merging the data in a better way, and so on. And then we even took the model to seismic velocities. We developed an effective stress seismic correlation, and then turned the model from a seismic aspect into a pore pressure volume, as well as producing our own pore pressure volume from within the model. So
Well, it
maybe that's
totally
a
makes
longer
sense.
answer than you were asking for. I don't know, but it's all about the model. It's all about the geology. So the
Well,
geology needs to go in.
yeah. Well, we have a question that kind of flows right into that. Inga Pettersson is asking, if you have an uplift, how would that influence the burial and charging history on the phase envelope?
Yeah, absolutely. So the question is that yes. So if you have an uplift and everything depressurizes, then yes, basically you're basically, you're going back up the barrel. You're back up the barrel history and reversing. So that certainly is something to factor in. The question though is that it's not really whether. You can't just assume that the basin drains when it's uplifted. So it's not automatic that it's going back up the same profile, compaction profile that it did when it was buried. And there are plenty of uplifted overpressured basins that demonstrate that, right? So you don't just have overpressure where there is where there is deep water rapid sedimentation. There's overpressure onshore as well, and in the Permian Basin, the Wolfcamp is phenomenally overpressured, the Wolfcamp Shale. So, 5,000 or 6,000 pounds of excess pressure there. And so, yes, uplift and erosion needs to be factored into the barrel history. But I would just encourage people to think about, it's not so much, don't assume that overpressure, the uplift and erosion drains the reservoir immediately or even necessarily, effectively.
Mm-hmm.
In a similar, I know in a similar kind of vein, again, talking of small molecules, there was a presentation I saw on the Israel, deep water Israel, all the biogenic dry gas down there. And the author assumed that because of the Messinian drainage, that basically the reservoir pressure also would drop in response to the reduction of the hydrostatic head there. But if those reservoirs are turbidites that don't outcrop anywhere, which they obviously don't because they're turbidites in the basin, then it's not necessarily the case that the pressures were reduced in the reservoir, right? Because if it
That's
can't
a good
drain,
point.
it can't get back to, it can't, if it can only drain at a certain rate determined by the overlying shales, then just because the water depth goes down doesn't necessarily mean the reservoir pressure goes down. So it's kind of a bit more complicated. I think that it's a great question. I really appreciate it, because I think it's often oversimplified and assumed that the reduction in overburden or reduction in water overburden in that case is immediately causes a depressurization. It doesn't necessarily. The other interesting thing as well is if you think about onshore basins where the reservoirs do outcrop, then there's a lot of old sort of folklore that we need to get out of our geologic thinking. And one of them is that you uplift a basin, you kind of quote unquote blow the seals by basically by removing the overburden. Patently, you don't do that because most of the world's petroleum is in onshore basins that have been uplifted and eroded, including some dramatic ones like the Appalachian Basin, where there's been uplift and erosion there for 350 million years or so, and yet the whole system's quite happily there. So actually, what happens then is that if the reservoir can drain, but the mud rocks can't, you actually end up with overpressured seals, which actually enhances the column capacity, which again explains why, as I say, the onshore basins there's no such thing as blown seals in onshore basins. If anything, it would actually improve the column capacity, because the shales can't drain quickly, and yet the reservoirs, if they outcrop, can drain immediately, and so you end up basically armoring all of the seals in the basin, because they have a differential water pressure compared to the well-drained sandstones or limestones, the reservoirs. So
That's
again, maybe
cool.
a longer answer than than you wanted. But
Well,
anyway,
now we go into speed rounds because we have 2 or 3 more questions and we only have a few minutes.
okay, cool.
Okay, so speed round question number 1. Martin Cassidy asks, have you looked at Nigeria? It appears that the sourced fluid is very gas rich.
Yes.
The oil is very lower ratio in reservoirs.
Yeah, yes, we have in fact, well, we haven't published it, but yes, we've done the UEP log like the ones I showed you for the Demerara Rise for the for the Eocene, the lower Eocene reservoir that's published in the paper by Chevron. It has a balance of oil versus gas expulsion. It is an oil-prone source rock, but it has a huge chaser of gas with it because its overall quality and hydrogen index, just like the Trinidad Shelf stuff. When you have a low hydrogen index, then basically you have low expulsion efficiency, so you crack a lot of the generated oil. So yes, Nigeria is a beautiful poster child for what happens when you have a sort of a quote unquote mixed oil and gas expulsive source rock. We haven't published that yet, but it's in our training classes that we give, and so the primary, as I keep coming back to, we've just not studied the source rocks enough in the last 10 or 20 years to as we should have done in order to understand the first order control. So that's a very simple first order control, is that onshore Nigeria is underlain by an oil prone but also highly gas prone source rock. And so when you look at there's 40 billion barrels of oil resources in Nigeria, but there's also 200 TCF of gas, which is a GOR of 5,000. So there's a lot of associated gas and gas cap gas in that system.
Okay, so we have time for one more. So Maria Gutierrez asks, I'm curious about what is being done lately about trying to update some of the geochemical methods, like the carbon-13 isotopes in gas light oil, since they were developed over 30 years ago. It seems that there's a lot of potential and it's being overlooked.
What a great comment. And this is something I've been trying to persuade people to do, and something that we're doing anyway. So into Excalibur, which is this Earth model, we actually have a modern geochemical module, which again has all of our latest stuff from biogenic gas to biomarker thermal stress indicators and Tmax inversion to thermal stress. The things that we do, I would argue, are so basically there isn't a piece of software that does modern petroleum system workflows as far as I'm concerned. So we're building it. So Explore Lab, in partnership with ourselves, are building that into that model. So if you just send us an email, whatever, if you're interested in following that up. But it's something I'm very passionate about. I think it needs doing. And it's kind of interesting that if you think about what the seismic, I'm not trying to shame everybody here, but this is something that may really drive it home to everybody, is that in 1978 and around 1980, when a lot of these, Rockefeller was invented and stuff like that, the seismic guys were doing fourfold seismic. So look at how seismic has changed in that time. Now we've got swirl surveys with ocean bottom cables and 3D depth processing and all that stuff, and yet geochemistry has really not changed in that time since fourfold seismic. So if you imagine going to a client and saying, oh yeah, I've got this old fourfold seismic, like, can I do a study for you? And you can imagine why geochemistry, unfortunately, is not as regarded as powerful as it could be. It's just because it's old and out of date. And so
Well,
that's a great point. Thank you.
Yeah, that's a good point. Yeah, and also, I mean, with the kudos to like Weatherford and Stratum, now Stratum, they do all the fingerprinting, but that's kind of challenging if it's deep water because, I mean, where do you get? I don't know. At any rate, I thank you very much for that comment and your Andy. So we
Pleasure.
have a couple more questions. If you could go to your final slide, I'd like to point everybody to your contact information because we don't have time for the last couple of questions. So I'd like to encourage people to go ahead and get in touch directly with Andy. There is his email. Whoops, it just went. There we
There
go.
you go. There you go. Right. Yeah. Yeah, and I can put you in touch with Jean-Marie at Explore Lab as well. But if you know if it's more on the sort of software side, so yeah, so right now that is a that is a available piece of software. Obviously, we're developing it daily because there's just more and more new stuff that we're cramming in there. But the U of H guys have an academic license, and so if you watch out for some of their products, including Daniela's when she does her much better tour of the UEP maps than I was able to do in a short time. You'll see all of that coming out in the Excalibur software. Yeah, so just watch out for that. If you're a member of that consortium, if you're not a member of that consortium, then please go persuade your manager or whatever. I mean, those guys are just doing some amazing stuff, and we're doing our best to stuff some sort of modern modern geochemistry and basin modeling into their workflows as they go.
Well, thank you. Well, everyone, I'd like to thank everybody for staying to the end. Sorry, we're a little bit over, but just this was fantastic, Andy. And I just really, really appreciate your sharing all this insight. It's incredibly valuable. So we'll definitely get this up and give everybody a link to it so they can watch it again at their leisure. And thank you again.
All right, my pleasure. Have a great day, everybody. And yeah, drop us a line if you'd like to learn some more. Thank you.
Perfect.